Our goal for this lesson is to create some scatter plots and be able to identify if it's a linear or non-linear relationship. Our grade 9 course focused on straight lines, no curves, no bends, no twists, absolutely straight like a ruler, and those are linear relationships. Any ones that do have bends or twists or some abnormalities happening to them are non-linear relationships. So our goal here is to be able to also draw a line or curve of best fit and use interpolation and extrapolation to predict values. Now these are words we used in grade 9 as well, interpolation and extrapolation. Inter, if you think of the word inter or the prefix inter in the word interpolation, inter is like inside, internal. So these are between or data values between points, poles, points on our graph. Whereas extrapolation, extra means beyond or outside of the poles or the points that were plotted. So if you have your line of best fit and you extend it, any values you predict beyond the given data set, that's called extrapolation. If you're predicting values between the given data value set that you have, then that's interpolation. Okay, a warm-up question here for you. Mrs. Logan's creating a square vegetable garden. So here's a key word right here. The idea is it's square. So we know by definition of a square that all sides are equal in length. Okay, and that's my vegetable garden in my backyard. For the various side lengths, calculate what the perimeter and the area of the garden will be. So perimeter, remember, is the distance around the outside of the garden. So if my side length is 1, I'm going to have 4 sides of 1 unit or 1 meter in length for a total of 4 meters. Then if I had a side length of 2 meters, I would have 4 sides at 2 meters each to make a perimeter of 8 meters. So you can finish that chart knowing the different side lengths and calculating perimeter. Area is the amount of space inside my garden, and area we know is length times width for a square. The length and the width would be equivalent, so if my side length was 1, I would be 1 times 1 or 1 square meter of area. Likewise, if my side length was 2, I'd be 2 times 2 or 4 square meters for my area. So again, you can calculate the areas for the various side lengths here. And then you're going to create scatter plots of each. And I've already set up the axes for you on these, which helps, but you still need to label the graph. You've got to put a title on it, you need to put axes titles on it, and complete your graphs there. So put the video on pause, do your work here, and then you can check it with the rest of the video. Okay, so I've added my perimeter formula. It's just 4 times whatever the side length is. Our area we already defined to be equal to the length times the width. For that formula, I've calculated my values there, and then you should create your graphs if you haven't done so already, which I will do on my next slide here. And I have a feeling it's going to get added to the beginning of the video here. So I am going to add this to the end. All right, so here I have my graphs created, and you'll notice the very first one, based on how I've set up the scale, every block is worth the same amount going up and going across. That produced a nice linear relationship. Now I apologize, I couldn't find a straight line tool on Explain Everything here, but I did my best to draw a straight line through those points. However, when I look at the area versus the side length for my square garden, I noticed that this is a nonlinear relationship. It has a nice little curve to it. So it's an interesting fact that perimeter has a linear relationship compared to side length, whereas area isn't linear. So in terms of describing my relations, the first one is linear. The second one would be a nonlinear relationship. Now use the curve or line of best fit to predict the perimeter and area of the garden if the side length is 8 meters. So if I want to create a side length of 8 meters, I'd be looking at my perimeter being side length of 8 meters, and if I follow that across, I know that my perimeter would be equal to 32. I mean, I could easily enough use the formula for this one, but that's only because this follows a predictable pattern to it. Now, if I look at the next one, you'll notice that 4.5 is going to happen halfway between. So this is an example of interpolation because I'm going between the given data set or given data values, and I got a value of around 20, maybe just a little bit more than 20 there in terms of area if my side length is 4.5 meters. So I think I meant I got interrupted, I'm sorry, while I was doing my recording here. My area is approximately equal to 21 meters. Let's go with that. If I look at my perimeter for this one at 4.5, it's looking like it's 18 meters. So this would be interpolation because the 4.5 is between given data values, whereas at 8 meters, we're looking beyond the given data values. And you can see I'm going to fall off the grid here, but it's going to be somewhere up here. And if I use my formula here, my area will be 64 for this one. So beyond the data set is extrapolation. Okay, and I need meters squared on area, and my perimeter has just meters as my unit. Now, the last thing we're going to do here on this page is we're going to actually go back to the first page and calculate the first differences in the dependent variable for each table of values. So remember, we're going to take a look at the y coordinates of my table of values, and we are going to see how much they increase or decrease by. So I'm going to flip back to the first table, and I really hope that this gets added to the end of the video and not to the beginning of the video with the first page. Okay, so I have my tables of values here. We're going to calculate our differences. So I'll just put diff for differences here as a short form. To go from 4 to 8, we are increasing by 4. So that's a first difference of positive 4. And similarly, if I go from 8 to 12, I'm increasing by 4. So my first difference is positive 4. And likewise, all the way down here, when we calculate these differences, we're going to get positive 4. Now, we already know from our information from grade 9 that if we get that constant first difference, we will have a linear relationship. Now, we know that the second relationship was not linear when we graphed it, so that means that these first differences should not be all the same. And to go from 1 to 4, I'm going up 3. To go from 4 to 9, I'm going up 5. To go from 9 to 16, we're going up 7, and so on here. So you can see that these are not constant, although they do have a pattern to them. And up 13. So they do have a pattern here, and that's an important pattern because what is happening here? We might notice that if I took the differences of the differences, so these are called the second differences. So second differences, these are all going to give you the same value this time. So this, to go from 3 to 5, we're going up 2. And to go from 5 to 7, we're going up 2. And each time here, we're going up 2. I'm going to ignore putting the plus sign on these. So when our second differences are constant, like this, we end up with a special type of relationship, which is called our quadratic relationship. And that's the focus of our next couple of units.